All right, accidentally hit stop recording, but we're back recording. Sorry about that. I've looked up the critical pressure, critical temperature, and the acentric factor for methanol and dimethyl carbonate. So methanol, critical temperature and pressure comes from the Felder, Rousseau, and Bullard textbook. I had to look up online what the acentric factor was. For dimethyl carbonate, I was able to find a literature paper that actually had the entire equation of state. It's called Thermodynamic Properties of Dimethyl Carbonate by Zhao, Wu, and Lemon. So I'm going to trust that resource. Pointing out just that all this stuff is as accurate as the data that you find. So you have to trust this data before you can go ahead and use it. While you're in school, I would probably, trust a majority of what you find. But when you get out into your jobs, if you ever had to do this, it may be worth it to maybe see if you've done the experiment yourself, want to get the critical temperature and critical pressure a little bit more accurate, because there is some disagreement, right? I found another resource had values for methanol that were a little bit off, but I decided to keep the ones from Felder, Rousseau, and Bullard. All right, next step is to go through calculating what B0 and B1 are for the two components. So for that, I need the reduced temperature. And the reduced temperature is the actual temperature divided by the critical temperature. So it's going to be 428.15 divided by critical. All right, let's make a column now for B0. Make a column for B1. And these are both going to be parameters for each one of the components. So B0 is 0.083 minus 0.422 divided by the reduced temperature. Oops, I forgot my equal sign. Equal sign. Divided by reduced temperature to the 1.6. Drag that down. And B1 is 0.139 minus 0.172 divided by critical. Forgot the equal sign again. Equal sign, reduced temperature to the 4.2. Enter. All right, now we've got B0 and B1. Let's now calculate B prime. So this is going to be B prime 1. This is going to be B prime 2. So B prime is going to be the quantity of R. And let's see, I was careful to keep my units in pascals and kelvins. So my value of R can be 8.314 times critical temperature divided by critical pressure. So what I'm doing now is I'm taking these three over to the other side, in case that wasn't clear. So I'm going to put these in parentheses and then multiply by B0 plus acentric factor times B1. And I've got a negative. Let me double check. Okay, that looks fine. Did not make a mistake. The only thing I'll mention that you can do to adjust this, so the units of this B prime parameter are meters cubed per mole. And just for simple, I find that I make less mistakes when I stick to strictly SI units. But if you wanted to, if you're uncomfortable with 0.00033, you could always convert this into centimeters cubed per mole and say you can multiply this by 100 cubed. So equals this times 100 cubed. And then if you're following along in the Dom and Visco textbook, you see that these numbers are pretty close to the ones that they give you. A little bit off, and I'm imagining that that is because of differences in the sources that they're using to calculate, or the sources that they found for critical temperature, critical pressure, and acentric factor. Because I mentioned that those can deviate a little bit depending on your source. So once again, this is always why citing your source is very, very important, because if you have a mistake there, you want whoever's reading it to be able to go back and say, this is where I got the data from. So this is potentially why I have an issue. So if I were doing this homework assignment, I would be very clear to say, hey, I got these critical temperature and pressures. Remember, these two are from Felder, Rousseau, and Bullard. This is from, I should be more specific on where I got this from. Let me look up real quick. This is from a list that was on the internet that it was pulled from Reed, Posnitz, and Poling, 1987, The Properties of Gases and Liquids in the 4th edition. And then these were taken from that literature paper that I cited that was titled Thermodynamic Properties of Dimethyl Carbonate, which was published in 2011 in the American Institute of Physics journal. Okay, pressing on, we've got B prime 1 and B prime 2. We now need to calculate B prime 1, 2. So I'm going to do that for both, right? Or actually, I want to make it a little bit clearer what I've got here. So I'm going to make another, I'm going to just move this over and say this is B prime 1, this is B prime 2, and this is B prime 1, 2. And just to format it nicely, to adjust it, I'm going to put it like that. And then also I will border it and shade it. So shading it always helps me in my mind kind of highlight it to me. Okay, B prime 1, 2, I said this is going to be the geometric mean. So I'm going to say this is square root of the 2 multiplied together. I4 times I5. And copy that formula over there as well. This should be negative, no? Yes, it should be negative here. And this is important to point out that Excel will give you the positive root. So I want the negative square root. And that is because if B1 and B2 are both negative, I want my cross term to be negative as well. And this is to be expected. B1 and B2 should be negative, and therefore B1, 2 should be negative as well. So if I take the square root, remember I could have positive or negative of that answer. So I want the negative one such that it matches. All right, next, where do I go next? I want to calculate the mixing B prime. All right, so I haven't calculated what the mixing B prime is yet. So I need to find that in my notes. Actually, I'm sorry, we don't have to calculate the mixing B prime. We've done that with B prime 1, 2. What I need to do now is use these 2 equations to obtain what the mixture fugacity coefficients are. So right next to my experimental data, I'm done with this now. This red box can go away. I've already used it. I'm going to now use this blue text in order to calculate what my mixture fugacity coefficients are. So I'm going to say phi hat 1, not phi raised to the power 1. Hopefully that notation's clear. This can get a little clunky when you're using Excel. Once again, as long as it's clear to you, it's okay, but this is another reason why when you look at somebody else's Excel spreadsheet, the way they number things or name things, it's always tricky to interpret somebody else's Excel spreadsheet unless they explain it explicitly to you. All right, so I'm going to use this equation for phi hat 1, and that is exponent. So I'm taking the exponent of both sides. Exponent of P divided by RT, 8.314, divided by 428.15. And this is bad modeling practice. I should have temperature in a cell, and I should reference the cell just in case I wanted to do a different temperature later. But since temperature is constant, sometimes it'll be a little bit more keystrokes, but when I'm going back and looking at my equations, it could be clearer to use the actual number rather than a cell reference if it's a number that doesn't change. So instead of writing 8.314 in a cell and then referencing that cell, maybe I'll just keep it as a number in order to increase the clarity. I want to put this in parentheses. So times B prime 1, and that's going to get $signed. And is it going to matter if, yeah, I want to keep it in the meters cubed per mole one. I don't want to use the centimeters cubed per mole because I use the gas constant for meters cubed. Again, I could use the gas constant for centimeters cubed if I want, but I don't happen to have that one memorized. Or I could convert it, but it's the same amount of work either way, I think. Plus y2 squared. So y2 is 1 minus y1 square times 2 times B1. Oops, made a mistake there. That should be B12. 2 times B12 minus B1 minus B2. Close out purple, close out red, close out black. Okay, so I've got a phi that is 1. And that is, it is somewhat comforting anytime I've got phi's that are close to 1. Doesn't seem like I made a mistake. Let's keep going. Phi 2 is exponent of P, I'm gonna do parentheses, P divided by 8.314 divided by 428.15. Sorry, I lost my train of thought for a second. Times B2 $ plus Y1 square times 2 times B12 minus B1 minus B2. Close out everything. Cool. Okay, now I need phi hat, or phi saturation. So phi 1 sat and phi 2 sat. So as I pointed out in class, if I have a pure component, right, so now if I want to calculate what phi 1, not phi 1 for the mixture is, that means that y2 is going to 0, which kills this entire thing, which is just B prime. And I also have to remember that at saturation, I have to use the saturation pressure. So phi 2 sat is going to be B prime times P sat divided by RT. So B1 $ times P sat. Now what is the vapor pressure for component 1? Again, I could look it up in Antoine's, or I could calculate it by Antoine's equation, or I could just use my experimental data. Always I want to use my experimental data. So I'm going to take the vapor pressure when x is equal to 1, which means pure component 1, divided by 8.314. Whoops. And I'm not done yet because I have to divide by 428.15. Don't like that negative. I've got it. So the negative comes from the B prime 1 being negative, but what I forgot is that I didn't take the exponent. So I have to do is equal to exponent of this. There we go. That makes more sense. Can't forget about the exponents. So you got to bring the exponent over to the other side. Same thing for phi 2. So it's exponent of B prime 2 $ times vapor pressure for component 2 $ divided by 8.314 divided by 428.15. Cool. All right, and now I could do a ratio of the phi's. So it's equal to 1 divided by phi sat 1. And, oh, that's interesting. I've got it. I've got my mistake, and I'm ashamed again. So I'm going to pause the video, allow you a chance to practice your troubleshooting skills. Maybe you've already have recognized where I've made my mistake, but see if you can highlight my mistake. Go ahead and pause. The answer is it's another unit error. So I've got pressure in kilopascals, yet every time I use a gas constant, I'm using 8.314, which is 4 pascals. So a quick way to fix this, once I've realized that I made this mistake, this is another useful hint. Option 1 is I could go back and every time that I have a gas constant, I could use the correct gas constant instead. This is why it's useful if you had R that is just in a cell, you could change the value of R, but I'm going to show you a quicker way. Instead of referencing a cell where P is in kilopascals, I am just going to, oh, maybe. Why is this not going to work? Oh, because I'm in a formula right now. I need to back out of this, undo, 8.314. Okay, I don't want to change any formulas. So I'm going to insert a column, and I'm just going to copy this data to preserve it, just so that I have it. But I'm going to simply make this column P in pascals, and make it this times, let's see, to convert kilopascals to pascals, I just have to convert by 1,000, correct? So I have to say equals, there we go. Now this is going to mess up my PXY data, but that's going to be okay. No, kilopascal. Yeah, I think this is okay. Oh, I see what I did. When I copied this formula down, it's copying the same value. So instead of the value, I don't want to multiply the value of 556. I want to multiply the cell value such that it changes as I go down. There I go. And I've got too many tick marks on this axis. I've also got way too many significant figures on this axis. I'll deal with that later. The point is that now we have, you know, let me double check this one more time. So now we've got phi coefficients that are going to 1 at a pure component, which is good, but I don't like how it dips below and then back up again. So I'm just going to double check and make sure I don't have any more mistakes. Okay, I'm back after maybe a 30-minute troubleshooting break. I realized that I put the negative there because I said you have to take the negative, but I didn't put the negative in the B1 too. So found my mistake. Once again, this is speaking to the point of sometimes it is very frustrating to find a mistake. Like I said, it's just been 30 minutes trying to find that mistake, and I will never make that mistake again. So now I've got my phi is decreasing steadily, which makes sense, and my both phi's are decreasing steadily. And I've got, this is phi hat 1 over phi sat 1 is going to 1 at pure component 1, which is good. And it's starting out at 1.1. So like I said, if this was close to 1 at all ranges for x, I would say that it's okay to use the ideal gas assumption. But because it's 1.1, not necessarily 1, that means that we have to use this virial expression approach. And this is the same for phi sat 2. And what I'm doing now with these, oops, I did the wrong one. This is phi 1, this is phi 2. What I'm doing now is what I suggested to you, that this equation is very large, so I'm breaking it up into chunks as much as possible. So when I go to calculate what my, I lost my equal sign there, but when I calculate what my gammas are, now instead of phi hat over phi sat, I'm just going to use this one cell as opposed to plugging everything in one big expression. That's going to make things a little bit easier. Let's see, I also need my molar volume. I never looked that up. So I need molar volume V underbar for the two components. So I have to pause and look that up or calculate it. Right, so I've looked up what the molar volumes are in the back of the Dom Visco textbook. They have data that's in centimeters cubed per mole. So I've just converted it to meters cubed per mole by divided by 100 cubed. All right, let's now use this equation in order to calculate our experimental gammas. I think we have enough information to be able to do that. So gamma 1 is equal to yi times p times my ratio of the fugacity coefficients divided by xi times p sat for component 1, which is down there, times exponent, and I'm going to need to remind myself to parenthesis this eventually. V underbar times P minus P sat, close parenthesis, divided by R times T. So 8.314 times 428.15. Close that, and I'm going to want other parentheses. All right, so now my denominator is in parentheses as well. Divide by 0, which is okay because that's a pure component. And it looks like I forgot to $ something. Oh, why am I referencing this cell? Probably because I forgot to $ the value in I4. So I4 $ it. Now let's see. All right, perfect. I've got a gamma 1 that's going to 1 at the pure component. So that is a reassuring sign. I'm going to do the same thing for gamma 2. So gamma 2 is 1 minus y1 times p. I want to make sure to take the Pascal one, times ratio of the fugacity coefficients divided by 2 parentheses 1 minus x times p set. Make sure to dollar sign that one, times exponent of molar volume, dollar sign that one, times p minus p set, close parentheses, divided by 8.314 divided by 428.15. Uh-oh, typo. This should be 1. Excel found an error, which means I'm not referencing, oh, maybe I am referencing the cell. So I made a mistake somewhere. I'm trying to find it. I've got it. I'm switching back and forth between my pressure units. So I need all my pressure units to be from the Pascal side. I think, so I actually made a mistake in my gamma 1. Wait. What is going on here? So I was saying that in my gamma 1 equation, I'm using the kPa value, but it worked, which is confusing. Let me see if I switch it over to Pascal's, whether it still works. I'm gonna just drag over all these. Okay, so that's not the problem. Why is, let me try this one. Whoops, simple mistake here. I've been going back and forth whether or not I do the divided notation. Because I did the parenthesis here, this has to be a plus, or a multiplication. All right, simple fix. Maybe not. I have another mistake somewhere. And I know that because I've got gammas that are a little funky. Actually, not a mistake. So it's okay that they're a little bit funky because the pxy is a little bit funky. So my gammas are okay. All right, the next step now is to use, I've already used the Virial equation of state. Now I need to use the Wilson model in order to find the experimental lambdas that best fit this data. So I think I've done a Wilson example before. It won't hurt to see another one. These are the expressions for the Wilson model activity coefficients. They are functions of 2 parameters, lambda 1, 2, and lambda 2, 1. Now remember that these are functions of temperature, but because we are trying to model the data for a temperature for which we already have the same temperature, I don't have to go through the trouble of finding alphas. So I'm going to say this is GE over RT experiment. And as the same way that I've done before, I'm going to calculate this based on my mixing rule. So x1 times ln of my experimental gamma, and it's not going to let me do it. I have to take out the endpoints anyway, so it's going to be x1 times ln of gamma 1 plus x2, 1 minus x1 times ln of gamma 2. Okay, drag that all the way down there. And now I'm going to attempt to fit this data using the Wilson model. So for that, I need to make initial guesses for lambda 1, lambda 1, 2, and lambda 2, 1. We'll make initial guesses of 1 for both. And this will be our GE over RT for the model. And we'll base it based off of Oh, wait, I need that expression. One moment. There's my Wilson model. So I need to say this is equal to minus x1 times ln of x1 plus lambda 1, 2 $ times 1 minus x1. Okay, minus x2, 1 minus x1 times ln of x2, 1 minus x1 plus lambda 2, 1 times x1. All right, let's see how we did. Getting all zeros, that is obviously because I've chosen 1 for both, which is ideal. If I have an ideal, then I don't have any excess Gibbs molar energy. Let me try a guess that's a little bit off. Let's say 1.5. Let's say 0.75. Just make an initial guess as that's at least on the right side positive or negative. Okay, I've got initial guesses that are somewhat close. Now let's make a squared error column and say this is equal to this minus that square. So difference in the exponent, the experiment and the model. And I'll copy that all the way down. I'll make a sum column, so equals sum of all these. Oops. This is my sum of squared errors, and now I'm going to use my favorite solver, so data solver, and I want to set the objective of that cell to be a minimum by changing the value of cells lambda 1, 2 and lambda 2, 1. No other constraints. I do not want to make unconstrained variables non-negative. Set it up to crunch, and okay, I've got myself lambda 1 and lambda 2, 1. Okay, I'm going to take a quick break here. I'm going to stop the video, and I'm going to come back in the third video, picking up right where we left off. This example turned out to be a little bit longer than I had anticipated, so I think I'm going to stop with this example for today, but there's going to be one more video where we come back and I actually tie it all together and recap what we've done. So all we've done so far is we've fit parameters to the model, but we still have to go about predicting. I still have to go about tracing my PXY lines in order to see how well this model fits. So like I said, that'll be the subject of the third video.